couple slides of this particular section. We'll cover some of the diseases. I'll kind of briefly go over that. I want to spend more time on more of the physiological mechanisms. What we're specifically going to go over today, as we talked about last Tuesday, today's Thursday. Tuesday, we talked a lot about gas exchange. We covered the first portion where we talked about ventilation, which was the movement of air into the lungs, moving in and out, inspiring and then expiring, or inhalation, exhalation, now that you guys know the mechanics of that. Now we've also taken into account the composition of air. And knowing that excuse me, oxygen is 21%, the air is 21% oxygen. We want to take a look at the partial pressures of oxygen. And not only are we going to look at the partial pressures of oxygen, we'll also take a look at the partial pressures of CO2. So with that, what we left with, by being able to calculate the partial pressures, we saw partial pressures of 160 for PO2 and PCO2 of 0.3. And given that, we saw the exchange of air from the atmospheric air with the alveolar air, and we saw PO2 drops from 160 to 100, and our PCO2 goes up from 0.3 to 40. And remember, that was the mixing of the air that took place, the rebreathing of air. There was a small portion that gets trapped in the atomic dead zone, or dead space, that gets recycled back in and out. And so after we account for all that, our alveolar air is 100 and PCO2 of 40. And so what we went specifically over, and what I reminded you guys to make sure that you study, is the exchange of air, or the exchange of our partial pressures. We know there's a partial pressure gradient pushing O2 into the pulmonary capillaries. Remember, our pulmonary arteries are delivering deoxygenated blood. That is a PO2 of 40 and a PCO2 of 46. This is deoxygenated blood coming back from the systemic circuit, making its way into the lungs through the pulmonary circuit. And we see a partial pressure gradient pushing O2 into the pulmonary capillaries and pushing PCO2, pushing the CO2 in the capillaries back into the alveoli. So this is external respiration. And external respiration that takes place, what we're doing is we're oxygenating the air, we're moving CO2 from the capillaries into the alveoli, and we're pulling O2 back in, following the same things that we've already studied. The pressure gradients allowing gas exchange to occur, oxygenating the blood, bringing us back to a PO2 of 100 and a PCO2 of 40. And so once that makes its way, returning back to the pulmonary circuit, back out into the systemic circuit, we'll see the delivery of oxygenated blood at a PO2 of 100 and again PCO2 of 40, where we see internal respiration taking place. Again, pretty much the opposite of what we saw in external respiration, we see in internal respiration, where we see the movement of O2 down its gradient into those oxygen-starved cells. At the same time, those oxygen-deprived cells are putting off a lot of CO2. And that CO2 is going to, again, move down its gradient from the cell's PCO2 into the systemic capillaries, and then returning back. So this completes the entire cycle. And the one thing that, the couple things that I talked about, we did talk about on Tuesday, is the red blood cells delivering oxygen. And then once they deliver their oxygen out to the cells, it's able to pick up CO2. Okay? And that CO2 delivery takes its way back to the lungs, and so forth. So essentially what's happening is that the hemoglobin, the 250 million hemoglobin molecules that are present in every red blood cell, is coming up and topping off that O2 to make sure that all that O2 is filled up, bringing it back down to a hypercapnic environment where we have high CO2. And then, due to that higher CO2, that CO2 is going to help unload some of that O2 back into the cells. So that mechanism of this unloading of O2 and then the unloading of CO2 that takes place in external respiration are some of the effects that we're going to be talking about, namely the Bohr effect as well as the Haldane effect. So, as I mentioned, I want to make sure that you guys kind of brushed up on all this material, because once we get into our mechanisms later on, I don't want you guys to get severely lost. All right, so with that, we saw O2 transport Just a quick background again. Once again, O2 transport. We see most of the most of the oxygen carried by the red blood cells, of which once the hemoglobin carries that oxygen, it's called oxyhemoglobin. And the mechanism that we're going to be able to see here is that O2, given that only 1.5% is dissolved in the plasma, hemoglobin is going to uncouple with this hydrogen ion. So natively, hemoglobin wants to be bound to hydrogen. That hydrogen gets kicked off with the presence of O2. O2 comes in, binds it to hemoglobin. We now have oxyhemoglobin, and it's this hydrogen ion that we're going to be taking a look at a little bit later. Now, for CO2 transport, you'll see that most of the CO2 is carried once again by the red blood cell. More of the CO2 is dissolved in the plasma because, as we mentioned earlier, CO2 is 20 times more soluble in a liquid than oxygen. But the remaining CO2 is carried through carbonic acid. All we need is that CO2 plus water to make carbonic acid. And that carbonic acid, we'll take a look. Once they differentiate, we've got our bicarbonate. We'll see the role of what bicarbonate's going to do. And then lastly, we're going to take a look once again at hydrogen ion. And then the last bit where the remainder is carried by hemoglobin in different attachment sites. So hemoglobin, as I mentioned, hemoglobin competes with O2 and CO2, or rather, O2 and CO2 compete for hemoglobin. So the mechanism, once we start to see hemoglobin in a CO2-rich environment, we're going to be able to see how it's going to push off O2. And then conversely, hemoglobin in an oxygen-rich environment will help unload CO2. So you've got these two that are going to be competing, and it completely depends on where we're going to be seeing that. And where typically would we see something like that? Where would we see a high carbon dioxide environment? The tissues, right? These tissues are using O2 to undergo cellular respiration, and therefore they're going to spit out a lot of CO2. And if you look at this entire section, where do you see a high PCO2? Right in the systemic capillaries. You get deoxygenated blood that's picked up all that CO2. It's going to take it to an oxygen-rich environment, which we know the lungs. And that's going to help this sort of power play between the two. All right, with that, now that we understand the mechanism, let's, at least we're starting to get into the mechanism, let's take a look at how oxygen loading takes place. This is the entire premise of oxygen saturation. If you're doing O2 sats in your clinic, this is basically what you're doing. We're looking at hemoglobin, and hemoglobin has 4 subunits, 2 of which are identical. We've got 2 alpha, 2 beta. That you don't necessarily need to know, but there's 4 spots that that oxygen can bind to, and it binds to each subunit due to that iron molecule in each one of the subunits. And as hemoglobin binds, you can see that it can bind up to 4 oxygen molecules, or 8 actual oxygen atoms, because as we know, oxygen is double bound together. So at each point, you can see the amount of saturation that takes place. How saturated is are each of these hemoglobin molecules? Here we have 1 out of 4 spots taken, so we can safely say that this molecule is 25% saturated. Here we have 50%, 75%, and 100% saturated. Now, what this represents, when we look at all of the hemoglobin molecules, we're basically taking an average of all the hemoglobin molecules and saying what percent saturation are there. Because if you're wondering, well, what happens when I see an oxygen saturation? Let me first explain what an oxygen saturation is. That's how you're accounting for all your hemoglobin molecules, how much of them are saturated with O2. As I mentioned, each can carry 4. Your normal oxygen saturation is about, not normally 100%, although you can see 100%, 95 to about 98%. With that, what does that mean exactly? So if we see, for instance, you see somebody with an O2 sat of 87.5, how do we get in between 75 and 100? Well, that means half of your hemoglobin is 75% saturated, and the other half is 100% saturated. And you take it right in between, that's about 87.5. So again, just kind of an average of all of those. It gives a good rough estimate of how saturated your hemoglobin is. And how do they actually measure it? Well, basically you use an O2 saturation machine. It's a fairly easy machine. It just shoots a little infrared beam and bounces right back into the machine, and the machine can read how bright that infrared meter is shining right back in. And that gives us an indirect measure of your hemoglobin saturation. That infrared actually absorbs, the red blood cells will actually absorb some of that infrared light if it's not bound to hemoglobin, and all it does, it gives us a good measure. So from that, now that we know how oxygen saturation works, we know how it takes an average of all your hemoglobin, just all that blood that's running through, we can see how much light is absorbed and therefore infer what your oxygen saturation is. Now we want to get into how those 4 oxygen molecules bind to the hemoglobin.
How did you get 87.5? Is it just an average or what?
So 50% of your hemoglobin is at 100%. The other 50% is at 75%. 100, it's right in between.
Okay.
So it's just a good mix between the two. Now with that, we want to understand how our oxygen molecules bind to that hemoglobin molecule. It's not like one just binds on, and the second one binds on, the third, and then the fourth just bind whenever they feel like it. There's, our hemoglobin molecules exhibit what's called cooperativity, meaning that when the first oxygen molecule binds, then the second one can bind. Then once the second one binds, then the third one's more likely to bind. Then once we get to the fourth, it holds on to it even stronger. Okay? So if I can kind of use a loose analogy, it's like you have a bunch of friends that are going someplace, everybody wants to kind of drive separately, but you get that one friend or you get that one person that kind of wants to drive people. Nobody really wants to get in somebody else's car until that second person says, yeah, you know what, all right, I'll jump in your car. Once that second person jumps in your car, then you get other people like, you know what, well, since now there's 2 people, let me jump in. Then the third and the fourth, and everybody kind of hops on. And then once you get that third spot, no, I'll stop on that analogy. That doesn't really work. But essentially, there's this affinity that hemoglobin has. Once an oxygen molecule binds, then the second oxygen molecule binds, they hold on fairly tightly. And what are they holding on fairly tightly to? The changing PO2 that takes place. And we saw where that range takes place, and we'll be able to see that on the next couple slides on how that relates. So with that in mind, we want to take a look at the oxygen hemoglobin saturation curve. How strongly does oxygen bind to hemoglobin given the range of PO2? And the range that we already saw, the PO2 is here on our x-axis. It goes all the way from 0 all the way out to 100. And the ones that we talked about where we saw a PO2 of 100, we saw this in the lungs. Where we see a PO2 of 40, typically we would see that in the systemic capillaries, just like we saw on this prior slide. A PO2 of 40. So this we could safely say is about deoxygenated blood. And I don't like using that term deoxygenated simply because our blood at that point in time is not really truly 100% deoxygenated. So we'll just call this muscle. Now looking at this, you'll see that our y-axis represents our hemoglobin saturation. So the points that we know where hemoglobin saturation, which we talked about, is 100%, 75%, 50%, and then 25%. This 25 represents 1 oxygen molecule binding, 2, 3, and then all 4 oxygen molecules bound to that hemoglobin. So while our y-axis represents hemoglobin saturation, our x-axis represents PO2. And so what happens when there's no oxygen, right? There's no oxygen at all in the blood, our hemoglobin isn't saturated. And what we know, as we mentioned in our prior slides, that the oxygen carrying capacity increases due to the presence of hemoglobin. So looking at that, as we start to see an increase in the dissolved blood, the increase in oxygen in the blood, we see that hemoglobin starts to saturate, right? So we expect an increased linear, well not linear response, but we expect an increasing response. As we increase oxygen, hemoglobin starts picking them up and holds on to it. Okay? So we're set on that, right?
Sure.
All right. So with that, where do we see 25% saturation taking place? We see that at a PO2 of 20, at about 20 millimeters of mercury. Whereas 50, at 50, that second binds to at a PO2 of 30. Where does the third one bind? That one binds at approximately 40. So we go from a PO2 of 20, 30, and 40. And then once we get to that point, we have about 75% saturation. And then it's not until we get to about 100 where our fourth binds, and that doesn't take place until about 100 millimeters of mercury. That's our fourth. So we see distinctly two different regions of this area right here. We see a really steep curve, and then we see a not so steep curve. So two distinct regions on that hemoglobin saturation curve. And these two different areas represent high affinity and low affinity. And the affinity in this case represents how tightly bound is that oxygen molecule to that hemoglobin. So take, for instance, starting from a PO2 of 100, where we typically see this in the lungs. If the PO2 in the blood drops down to 90, 80, we see that we're still fairly up there. Most of our hemoglobin molecules are still saturated. Our PO2 can drop down to 80, 70, and we're still fairly saturated. So if you were up in the mountains somewhere, right, and we know that 21% is still oxygen, but the pressure up there, the atmospheric pressure is low. That means down the line, if atmospheric partial pressure of O2 is low, then alveolar is going to be low. And let's say the alveolar air is about 75, the alveolar PO2 is about 75 millimeters of mercury. We're more in a hypoxic environment. That still means your hemoglobin hasn't let go of that oxygen, that fourth oxygen molecule. It's still holding on tightly, hence the high affinity. It's not until we get up to about 60 that we're about 90%. So we still have quite a bit of wiggle room for our hemoglobin to hold on. So take into account, for instance, let me look at people with respiratory diseases of some kind, where they have a harder time getting in oxygen. You see people with COPD, emphysema, they have a harder time breathing, and their PO2 is going to drop naturally because they have a hard time getting air in, not so much a hard time with their hemoglobin. Why? Because their PO2 can drop in their blood due to that low partial pressure, and yet their hemoglobin remains saturated. Their hemoglobin works, it's just they have a hard time getting air into their system. So that high affinity we've now described. What does it mean with low affinity? That means by the time we get to about a PO2 of 40, that hemoglobin has unloaded its first O2 molecule. So I'm going from none unloaded to one unloaded. Then we dip down to a PO2 of 30, that second one jumps off. We get a PO2 of 20, that third one jumps off. So there's not much wiggle room over here on that lower end, hence the low affinity. So basically, in between the third, second, and that first, hemoglobin just kind of lets it go. This should make sense. If our PO2 is dipping down fairly low, somewhere like right around the muscle, if our PO2 drops from 40 down to 30, that means our oxygen levels are low in that area. We're in a hypoxic environment. And we want hemoglobin to do exactly that, to unload those oxygen molecules. Make sense?
So it's better to lose 3 than 4, in a way, because you...
Better in what sense?
Oxygen.
Well, it's not necessarily better. It's just it's on the basis of need. If you're at a PO2 of 40, right? Well, let's play that back. Where did we see a PO2 of 40? In the tissue, right? A PO2 of 40. If I'm at a PO2 of 40, that means each molecule of hemoglobin has only gotten rid of how many O2 molecules? Let's take a look. Right up at 40. We're at 75% saturation. So I ask again, each hemoglobin molecule has gotten rid of how many oxygen molecules? One. So once again, going back, hemoglobin has 4 oxygen atoms the entire time, or oxygen molecules. Hemoglobin's still holding onto those 4 oxygen molecules. Still holding onto those 4 oxygen molecules. Finally, we're in a hypoxic environment, and I've only unloaded 1 molecule. I'm coming back, and I only have 3 attached. 3, 3, 3, coming all the way back up. Oh, now I'm in an oxygen-rich environment, and I'm naturally going to top off. I'm going to pick up that 4th oxygen molecule and bring it right down. So that example that I mentioned last time, where we see our, and let's think of that tissue now working overtime. You're running really fast. You're using all that oxygen. You're churning a lot of CO2 out. That's going to decrease your PO2. So your PO2, let's say, is 30. And your PCO2 is about 50. Let's take it back. When your PO2 is 30, your hemoglobin molecules have dumped off 2 oxygen atoms. Right? So now it's dumped off 2 oxygen molecules. It's still going to go back through the pulmonary circuit and pick up the other 2 in an oxygen-rich environment. So again, as our active tissues, whether this is skeletal muscle or anything else, anything that's consuming O2 in order to undergo cellular respiration, we're going to see hemoglobin dumping its oxygen molecules. So with that, now we see our low affinity, we see our high affinity, and we've been able to explain that. So the core principle out of this entire thing that I'd like you guys to be able to understand from this is that as PO2 in the blood drops, we see where we go from right all the way down to left. Hemoglobin is releasing oxygen to the tissues in the capillaries. They're releasing oxygen in order to offset a hypoxic environment. And this is the mechanism as to how it works. That's your basic understanding. All of the low affinity to high affinity makes it a little bit better. And then, all we've been talking about this entire time is how oxygen interacts with hemoglobin. We still have to account for other things in an active muscle tissue. It's not just using a bunch of O2, it's also spitting out CO2. It's also spitting out hydrogen ions. How does that affect the hemoglobin saturation curve? And that we'll describe on the next slide, the next couple slides over. What questions do we have about this? Yes?
So when it's like high and low affinity, basically you're releasing O2 from the hemoglobin.
Yeah.
Okay, so it goes from like, start from 100, that's releasing the first one, second, third, fourth.
Yeah.
And then when you're going up, that's you are picking up oxygen?
Yeah, you're picking up, the hemoglobin molecules are picking up oxygen molecules. We can see that because we're increasing the oxygen saturation. As PO2 increases, hemoglobin saturation increases. That's the basic principle there. But where it actually picks up, you can see a PO2 of 20, 30, and then 40. Do I have to have you guys memorize at which point do we see saturation? Not necessarily. I'd like you guys to understand the relationship. And the relationship here is that once we start to get to a point where we're in a hypoxic environment that is less than a PO2 of 40, we see quick unloading of those oxygen molecules. So maybe, hold on, give me a second. If I can take that analogy of those 4 people in the car, where am I going with this analogy? All right, so I've got 4 people in the car, right? Because that's basically what a car is like. You've got 4 available slots. Once you get that, you might have a hard time getting them out of the car, depending on whatever this might be. But finally, when you get that one person out of the car, then the other two, the second and the third and the fourth are more likely to jump off.
So like after going out drinking, and then the first one moves off.
I wanted to use that analogy, but I didn't really want to promote that, so you said it, not me. So that's basically what we're getting at. That's your way of looking at the unloading that takes place. It's not like all four just kind of just jump on whenever they want to. They don't equally just jump on. There's a period where there's low affinity and there's a period of high affinity. So you should be able to kind of relate those in a hypoxic environment versus an oxygen-rich environment. You see that we have quite a bit of wiggle room where hemoglobin won't let go. Okay? So this is, any more questions on this? Okay, so now we have that principle. This, now that I look at it, I don't really know why I have this on there because it's basically the same thing. So all of that is written off to your left. All right, so now, as I mentioned earlier, we've only explained the relationship between O2 and hemoglobin. But as I mentioned, hemoglobin has an affinity for both O2 and CO2. Right? But the affinity between the two, they compete. You have, as I mentioned earlier, hemoglobin that wants to bind to O2. In an oxygen-rich environment, hemoglobin wants to bind to CO2 in a CO2-rich environment. And typically where you see one or the other, in an oxygen-rich environment like the lungs, we typically have high O2 and low CO2. Therefore, it makes sense. Hemoglobin has more oxygen molecules to bind to because there's less CO2. In an environment where you have a hypoxic environment like the tissues, you typically have more CO2 and less, more CO2 and less O2. So naturally, hemoglobin wants to bind to CO2. So with that in mind, let's take a look at our next. And actually, there's another molecule that comes in that hemoglobin wants to bind to even stronger. Does anybody know what hemoglobin wants to bind to more? Iron. Well, iron is a part of hemoglobin. Think of another gas.
Nitrogen.
Nitrogen? Now, nitrogen is actually an inert gas. It actually, carbon monoxide, says a respiratory therapist. So carbon monoxide comes in. If carbon monoxide is into the mix, carbon monoxide, hemoglobin wants to bind very tightly too. And when it binds, it holds on fairly tightly. Hence why you see the old school ways of suicide. People would I don't know, close off their garage and turn the car on, keep it running. That carbon monoxide comes in and can bind too. Also other things too, I remember reading once on, where did I read this? It's a long time ago on Reddit actually. And one of the things on there said, it was like people would reveal their craziest secrets, and Reddit has a lot of anonymous postings. And one of that person that said they owned a house and they were renting it out to a family of 5, and they were having issues with their water heater. So so he went over and he was working on the water heater, and he plugged one of the exhaust pipes. He was trying to get it to work, so he plugged the exhaust pipe. He finally got it to work and then kept it running. And he's like, okay, everything's fine. And then after he left, apparently there was a 911 call because all 5 family members died in the house. And they were doing a search, and he came to the house, the owner came to the house, and he was just like, how did this happen? And so he starts going around the area he was working, and he looks at the rag that had blocked off the exhaust pipe, and he pulls it off, and it became apparent to him that that's the cause of death, because they all had died of suffocation. So that was a secret of his, which I remember reading, and I was just like, okay, this is enough internet for the night, I'm done. Went to bed feeling really bad about that. You also read about people that have put barbecues inside their house.
Oh, yeah.
Why would you do that? Because charcoal puts off a bunch of carbon monoxide. Carbon monoxide, there's a reason we have carbon monoxide monitors, because it's really a silent killer. There's no odor to carbon monoxide. You don't know it's hit you until you're just not able to function anymore. And it competes. Carbon monoxide binds to hemoglobin and can't bind to either CO2 or O2 after that. So keep that in mind. Make sure yeah, let's not spin into the morbid. We're kind of going morbid into a 3-day weekend, so I'm gonna take a step back from that.
I heard that the reason they say when you're driving in traffic and you feel sleepy because of that gas.
Huh? Yeah.
When you feel sleepy in traffic, you know, there's a lot of carbon monoxide.
That's where you just text and watch movies and keep you awake. Actually, that was happening on my way over. I was just like annoyed. I'm like, why is there so much traffic?
Oh my God.
And I'm looking at people. I'm like, this dude was just straight up watching YouTube on his phone. And I'm like, are you serious?
Well, you just drive a Tesla, it's okay.
So I had to text my friends. I'm like, are you serious? Look at this guy. And so I took a photo. What is this guy doing?
Okay.
All right. So hemoglobin binds to O2 and CO2 depending on which gases we're more rich in. Okay? So now let's take a look at, again, the effect of that oxygen saturation curve in response to increasing O2, which we already know. As oxygen PO2 increases, hemoglobin saturation increases. And that's what we see with this black line. That's the same saturation curve we would see. Now, in response to other variables, things like increased CO2, increased hydrogen ions, increased temperature. These are all byproducts of cellular respiration, right? Increased temperature? Well, yeah, because we're producing ATP, and due to the second law of thermodynamics, those muscle tissues are producing heat. So how is that going to affect hemoglobin? Hydrogen ions, again, coming off from cellular respiration. What are we doing with those hydrogen ions? And then CO2 is going to affect. So typically with that, the general principle of what's happening is a shift to the right. This is our black curve, which is our normal oxygen hemoglobin saturation curve. Now exposed to these same variables, where we have high CO2, high hydrogen ions, or high temperature. So this would be hypercapnic, this would be acidosis, or this would just be increased temperature. This would shift the whole process to the right. Now, let's take into account those other principles that we just talked about earlier. If hemoglobin is bound to O2, right, and we start introducing more CO2 into the mix, CO2 and O2 compete for hemoglobin. So naturally start to increase the amount of CO2, you're going to get more hemoglobin that will bind to CO2. Or, in other words, another way of looking at it, hemoglobin is going to want to unload, and as we unload, we're going to see that the saturation is going to drop. That should make sense. With a drop in or a shift to the right, we'll see our oxygen saturation drop, and that is the Bohr effect, which we'll describe in a little bit. Now, looking at what happens with temperature. With hemoglobin as a protein, it's coming in there and it's held onto those oxygen molecules. Increase the temperature, we're increasing the kinetic energy of those of that oxygen molecules that are bound to each of those 4 oxygen molecules. Therefore, if we increase temperature, one of those oxygen molecules might just fly off. Technically, that doesn't necessarily happen, but oxygen is more likely to leave. So therefore, once again, a shift to the right. And then lastly, hemoglobin, again, a protein, exposed to hydrogen ions. Remember what we mentioned way, way, way back when? Take a protein, expose it to hydrogen ions, we can start to denature that protein, meaning we're changing the configuration a little bit. While we're not causing that much hydrogen ions in there, it's still going to affect the binding of oxygen to hemoglobin. Again, a shift to the right. Anything else? The exact opposite of that, where we have hypothermia, hypocapnia, low CO2, or alkalosis, a decrease in hydrogen ions, is going to shift it to the left. So let's take a look at what that exactly means. What does it mean to shift to the right? So this is what we illustrate is called the Bohr effect. That the decrease in pH, or the increase in hydrogen ions, as we described earlier, shifts the O2 hemoglobin saturation curve to the right. So with that, as I mentioned, a shift to the right. Now, I'm going to draw the points that we mentioned earlier, where let's take our PO2 of 40. At a PO2 of 40, we saw we're at 75% saturation. Again, that means hemoglobin is holding on to 3 out of 4 oxygen molecules. Now start to increase the CO2. Well, actually, before I take that, whenever I move down the hemoglobin saturation curve, I'm going from 100 to 75 to 50 down to 25. That means our hemoglobin molecule is dumping off 1 oxygen molecule, dumping off 2 oxygen molecules, dumping off the 3rd oxygen molecule, and at 0, we're dumping off that 4th oxygen molecule. So it's safe to say that as we move down the hemoglobin saturation curve, we're getting oxygen unloading. And if we're at starting off from 100, a PO2 of 100, PO2 of 100, no, that's not the straightest line. From here to here, when we go from a PO2 of 100 down to 40, we go down from 100 down to 40, we get our hemoglobin that unloads 1 oxygen molecule. Now, the shift to the right is exposure to increased CO2, increased acid, or increased temperature. And then, what exactly is this 2,3-biphosphoglycerate, BPG? This is one of the byproducts of cellular respiration, specifically glycolysis. So if you have one of your glycolytic byproducts in there, you better believe that that tissue is trying to produce ATP. So if it's trying to produce ATP, it's definitely producing ATP. Therefore, it's increasing temperature. Therefore, it's increasing the amount of acids. And it's definitely increasing the amount of CO2. So with that, we see that this shifts the curve over to the right. And what does that mean? That means now at a PO2 of 40, and let me draw this in a different color. Choose green. At a PO2 of 40, we see a decrease in our hemoglobin saturation. So that at the same range, from 100 down to 40, we saw in the absence of CO2, or in the absence of all these variables, we would expect our hemoglobin molecule to dump off only 1 oxygen molecule. Now, start to move towards the tissues, where we get increased CO2, increased acid, increased temperature, and some BPG in there. This decrease that we see at the same PO2 of 40 brings us down to a hemoglobin saturation of at about 55. Close to, let's even just say 50. So therefore, to sum what I'm trying to say, is that in the presence of CO2, let's just say CO2, in the presence of CO2, now our hemoglobin molecule is now dumping out 2 oxygen molecules instead of 1. So I'll play that one more time. In the presence of CO2, our CO2 and O2 compete for hemoglobin. In the presence of CO2, we're going to get more oxygen unloading taking place because hemoglobin is now unloading O2 in the presence of these factors. That effect right here, this effect, this extra effect of oxygen unloading that takes place from 75 down to about 55 is the Bohr effect. So it's not enough just to say that there's a shift to the right. Because if you say shift to the right, what does that mean? But looking at a constant PO2 of 40, where we see in the tissues, we see increased oxygen unloading. What questions do we have about the Bohr effect? Yes?
Just about the hemoglobin, is it, because it's a protein, is it because it changes shape too? Is that why it becomes more affinity, has more affinity towards oxygen? Like, as it loses a couple oxygens, does it slowly kind of change its shape to be more likely to pick up CO2?
Technically, yes. It's a rough explanation of what we're trying to get at. It's just when you look at, let me use another example. Take a hemoglobin molecule, and that's cake, for instance, right? You take boys, and those are the O2. Girls are the CO2 molecules. When there's more boys around the cake, most likely boys will be bound to the cake, right? As opposed to, this isn't working?
No.
No?
I just want cake now.
Yeah, so now that I think about it, got me hungry. So technically, to answer your question, what's happening with hemoglobin is the affinity is really, when hemoglobin binds to its oxygen molecules, the first couple, it will bind as long as there's an appropriate PO2. But once you get to the third, there's a slight configuration that happens with hemoglobin that holds on tightly up until you get to the 100, PO2 of 100. So slight configuration, but that's not really the heart of what we're getting at. It's really just, are they saturated enough? And we see at the low PO2 ranges, we see a low affinity for oxygen molecules, as opposed to the range, by the time we get from 40 to the range of all the way to 100, that's where we lock onto that fourth oxygen molecule. Did that help a little bit? I know we didn't thoroughly answer your question, but okay. And then again, that's only describing O2 and hemoglobin. The Bohr effect talks about the other variables that come into play, that the more physiologically relevant variables. Eli?
So I just want to confirm, so basically with the Bohr effect, if you see a decrease in pH, less hemoglobin will bind to oxygen, less oxygen will bind to hemoglobin?
It's not, don't think about it from the perspective of oxygen binding to hemoglobin. Think of it as oxygen being released from hemoglobin. So play that again, one more time. Say your question one more time.
So, okay, so with a decrease in pH, and we're
Okay.
looking at a constant of 40 at oxygen, would it be, basically the threshold be less when the oxygen, like, delivers from hemoglobin? I don't know.
Let me phrase what you're trying to say. With a decrease in pH, either a decrease in pH or an increase in CO2, I'm just going to throw that one in there. With an increase in CO2, hemoglobin is going to be less likely to be bound, well, no, I want to rephrase that. Hemoglobin is more likely to release oxygen, release more oxygen in response to an acidic environment or in response to a more hypercapnic or more CO2. Right? Because that's what hemoglobin's supposed to do. It's holding on tightly to those 4 oxygen molecules. And it's not really going to do it until we get to a PO2 of 40. Okay, now it's saying, okay, now I can get rid of that 1 oxygen molecule. Oh no, but also I see a lot of CO2 around. I see a lot of hydrogen ions around. That tissue probably needs a little bit more oxygen, so I'm going to go ahead and unload a little bit more oxygen for them. So it loosens up that oxygen saturation curve. And in fact, what it kind of does, it makes it a little bit more linear. So you lose that linearity, kind of like what Pamela was saying a little bit earlier. We get an area of low affinity, we get an area of higher affinity. By decreasing the affinity altogether, we're releasing more oxygen in response to these variables.
So those factors have to play an effect on Bohr's effect, right?
That is the Bohr effect. The Bohr
All
effect.
of those Bohr, right?
Yeah. So these come in to cause a shift to the right.
And then it could be either one or it has to be all.
It could be all of them.
All of
In
them?
fact, in an active tissue, it's actually all of these that are affected. But if you were to take an experimental situation and take that hemoglobin and say hemoglobin is naturally binding to its oxygen, and start to introduce these one by one, and you'll see that's going to affect the saturation curve. Because what we've been talking about this entire time for the O2 saturation curve, all that's in, the only factors involved here, O2 and hemoglobin. That's it. How does hemoglobin bind to its oxygen molecules? That's how it binds. But now you've got other competing factors, like CO2. CO2 and temperature and acids, and that affects it too.
So basically.
Hence where my cake analogy came in, but nobody got it.
Releasing oxygen your temperature is high,
I got it
you
out there.
have
Fever.
fever,
Yeah.
just like your
No,
hemoglobin
you didn't get
in
it.
order for like your muscles to work or for the fever to go away.
Not necessarily for the fever to go away. I don't want to. That's why I didn't really like the explanation of fever on there. It's more situations where tissues need oxygen. If tissues are going in and they're using that oxygen molecule to generate ATP.
So like exercising.
Yeah, exercise. So the effect of exercise will unload more oxygen into your tissues.
That's pretty much what the more effect is.
That's exactly it. If you were to hit it in a nutshell and sum it down, like a quiz question or a test question or something like that, that would be it.
So what did she say, sorry, about?
Something about a test question and a
And
quiz
exercise.
question. So the effect of exercise, the effect of increasing exercise, where you increase the amount of CO2 or temperature, is going to unload more oxygen.
So you're releasing more oxygen.
Yeah, the hemoglobin is releasing more oxygen so that the tissues can use it. Okay? Everybody on the same page? All right, so now I want you guys to take that entire principle right there and let's flip it around a little bit. We've been talking about the oxygen saturation curve in response to CO2, acid, and temperature. Now, as I mentioned earlier, hemoglobin can also bind to CO2. As I mentioned in this prior slide, 23% of that CO2 is bound to hemoglobin. The other portion of it, the other 70% of the bulk of it, is through carbonic acid. But still, hemoglobin wants to also bind to CO2. So let's take a look at the Haldane effect. The general principle here is that there's less O2 when there's less O2 carried by the hemoglobin, more CO2 can be carried. Hence that cake analogy. When there's more girls than boys, there's more girls bound to cake analogy. I'm not going to give up on that one. I got to So with that, hemoglobin bound to O2, hemoglobin bound to CO2. Here we see our hemoglobin wanting to bind to more CO2 than O2 in a hypercapnic environment. So what we want to look at is the principles of PCO2 with total blood CO2. So the response here, looking at this, with increasing PCO2, right? Where do we see increasing PCO2? Maybe somewhere in the systemic capillaries, somewhere in the active tissues. Where do we typically see a lower PCO2? We see that in the lungs. So I'm going to first draw that out. Lungs, and then muscle. As the partial pressure of CO2 increases, remember our law that we mentioned earlier, that the more CO2 that's dissolved in the blood, we see a linear increase in total blood CO2. And that should make sense. The higher the partial pressure of CO2, the more that's actually dissolved in blood. So we expect a linear response with that. Here we see the response where we have PO2 of, and we're just assuming, again, the linear response between CO2, PCO2, and total blood CO2. That's our green line. Now, as I mentioned, hemoglobin is going to play a factor in this. Once we start to increase the amount of PO2, and we're going from a PO2 of 0 here, and going to a PO2 of 40, right? So now we're starting to increase the amount. All this right here is increasing the amount of O2. All this is increasing the amount of O2. And if deoxyhemoglobin is bound to carbon dioxide, and I'm now increasing the amount of oxygen, that means that oxygen is now starting to compete for those binding sites. And if it's competing for those binding sites, that means more CO2 is released. And therefore, our total blood CO2 drops. So let's take a look at it from a different perspective. Same way of drawing it out. This is our blood CO2. This is our PCO2. There should be a linear increase in total CO2 and PCO2. And as I mentioned earlier, PCO2 of 46 and then 40. Again, you don't need to necessarily know the numbers here to understand the principle. So high CO2 will be in the muscle. This will be in the lung. Now, when we start to take a look at the effect of oxygen, the more oxygen there is, the less the more oxygen, the less our carrying ability of CO2. The less CO2 we can carry in the blood. So we expect a decrease in this line. And what that line looks like is this. And that should make sense. The more O2, the less CO2 in the blood. Why? Because hemoglobin is wanting to bind more to oxygen now. So if hemoglobin is bound to oxygen, there's less CO2 bound to that hemoglobin. So we expect a decrease in that. So from here to here, and once again, let me draw in green. From here to here is our CO2 release. And again, we're going from muscle, and once that blood makes its way all the way out to the lung, this is the amount of CO2 that's released in the lungs. But due to the effect of increased oxygen, where we see in the lungs, we typically have higher oxygen levels. We see an increase. I'm going to go back in red. We see where we're actually starting off on. At the same level right here, we see not only from here to here is how much CO2 is released, but all the way down to this next line, we see at that PCO2, we see an increase in the amount of CO2 release. So we're going from back over here at a PO2 100 all the way down over here. We get excess CO2 release. So this extra CO2 release that happens in the lung is the Haldane effect. And again, the Haldane effect is saying that due to the increase in O2, we're going to see more CO2 release. Again, very core principle behind it. From the perspective of hemoglobin, with increasing O2, we get more CO2 release. That's all that's taking place. Okay. And again, here comes our hydrogen ion, because technically what's taking place is that that hydrogen ion will play a factor, because that's going to come into carbonic acid, which I'll show you in the next slide. What questions do we have about the Haldane effect? Cool, because I got a video for you. I hope it works. I hope it works. And I really hope it works. Come on. Come on. Okay. Give me a second. And let me pull up another slide. Actually, you know what? It should be in Canvas. I'm really working on this. I don't have internet connection. That's why. That's why. Give me 15 seconds, 20 seconds. 30 seconds. Do you guys have problems connecting to the internet here? Still? All the time. There we go. Come on. Come on, video. Four effects. The guy that I like the most that explains all this. I'll send it to you guys. How about that? I'll send it to you guys. The one that I want to send you that explains it really well is a guy named Salman Khan, who's from the Khan Academy. Does a really good job of explaining the Haldane effect and the Bohr effect. Obviously a lot better than I can. But nonetheless, he comes up with this image right here and draws it all out. But he took all these ideas from me. This is all my drawings. I didn't get any royalties to it, but nonetheless, he's making millions of dollars for it. All right, so now that's our summary. Let's take a look at, down to a molecular level, what's specifically happening. Now this is the roadmap of what's happening in external respiration and internal respiration. And in external respiration, again, taking place in the lungs, we get high O2 and we get low CO2. So let's explain first what's happening in external respiration. And we're all going to start with our first oxygen molecule. So our oxygen molecule is fairly rich. We got a bunch of oxygen molecules in the alveoli. And it's going to diffuse across down its concentration gradient from the alveoli into the surrounding interstitial fluid through the pulmonary capillary wall. So all of this is happening in the lung. Well, let's be specific. This is alveoli. This is in our pulmonary capillary. So as O2 diffuses into the interstitial fluid, moves its way through the endothelium, dissolves into the plasma, we get 1.5% that will remain in the plasma of all total oxygen in the capillary. The others, again, hemoglobin is going to come in and bind to, or hemoglobin is going to come in and assist and carry the remaining 98.5% of that oxygen. So as that oxygen diffuses into the red blood cell, where we get 250 million hemoglobin molecules, a hemoglobin molecule that's initially bound to a hydrogen ion will come in and bind to that oxygen molecule. And that binding to the oxygen molecule will kick off that hydrogen ion. Okay? That hydrogen ion, what is it that hydrogen ion going to do? Once we get that increase in hydrogen ions, we have a buffer. And that buffer is bicarbonate. Anytime you're going to see acidosis, our bicarbonate is going to come in and buffer it. So our bicarbonate ion, which diffuses from the plasma, makes its way into the red blood cell, binds to that hydrogen ion. Once you have that hydrogen ion bind to the bicarbonate, you make carbonic acid. Carbonic acid then turns back into CO2 and H2O, carbon dioxide and water, by virtue of that carbonic anhydrase, a molecule that we'll be or an enzyme that we'll be talking about quite a bit. Carbonic anhydrase facilitates that conversion of carbonic acid into CO2 and water. That CO2 then diffuses out of that red blood cell into the plasma, and then from the plasma down into the interstitial fluid, and then back into the alveoli. So with O2 comes off CO2. Now, because our hemoglobin molecules are binding to O2, any hemoglobin that was bound to CO2 is now going to start binding to that oxygen and will unload that CO2. So again, that hemoglobin that's bound to CO2 in response to high oxygen levels in the lung is going to release CO2. That excess release of CO2 is the Bohr effect. That's what we're seeing right here. That's excess O2, excess O2, and that release. Oh, sorry. Let me take that back. That's the Haldane effect. Let me go back. That excess CO2 released is the Haldane effect. Normally we would go from our total CO2 content, and then we release that CO2, and due to the increasing amount of O2, again, that increasing amount of O2 is going to unload that CO2, which is going to contribute to more CO2 coming off that hemoglobin, diffusing into the plasma, diffusing into the interstitial fluid, and then making its way into the alveoli. So that, again, is the Haldane effect. Now, looking at what's happening in internal respiration, again, almost the opposite of what's happening. Take a look at all the players. You'll see O2, O2, hemoglobin, hemoglobin. You'll see our carbonic anhydrase, and you'll see, again, our hemoglobin bound to CO2. Now, in a hypoxic environment, such as the tissues, we have our tissue cells pushing out a bunch of CO2. That CO2 is going to, again, diffuse out into interstitial fluid, into the plasma. CO2 is going to diffuse into the red blood cell. CO2 now has two ways, of which 23% is going to bind to hemoglobin. Once hemoglobin binds to CO2, we'll see hemoglobin, more oxygen release. Where do we see that take place? We actually see it on the carbonic anhydrase side. So CO2 diffuses across, now it mixes with the water that's present in the red blood cell, turns to carbonic acid. That carbonic acid, again, differentiates into bicarbonate. Bicarbonate then ships out into the cell where it becomes our buffer in the blood. That remaining hydrogen ion comes in and competes, comes in and binds to that hemoglobin, unloading that O2. Once that O2 is unloaded, it diffuses down its gradients back into the tissue. So again, playing that back up. All this right here is the Bohr effect. And once again, tissue cells that are high in CO2 that's getting released will get taken into the red blood cell, which will affect the hemoglobin already saturated. So in the presence of hydrogen ions, in the presence of CO2, in the presence of temperature, that will unload excess O2, which is the Bohr effect. We go from here down to this effect with a shift to the right. That released O2 then diffuses off into the tissue. Even simpler. In the presence of CO2, hemoglobin releases O2. What questions do we have about that? This whole thing about the chloride shift, again, you don't need to know the chloride shift. It's whenever you have you have an anion that leaves the cell, you got to have another anion that comes in to balance it out. Otherwise, if you keep purging out bicarbonate ions, it's going to keep getting more and more positive on the inside, which is not supposed to happen. Red blood cells got to remain electrically neutral. These last bits I'm going to kind of breeze through, because what we're doing now is talking about the autonomic regulation of breathing. And most of this you can pretty much read on your own, but in order for us to save time and work on our lab for the day, I did print it out, yeah. We do have a Respiratory System somewhere. I'll find that for you guys. Medulla oblongata pretty much governs the, has the same respiratory centers. We saw the medulla oblongata that receives all this input, all the sensory input from the proprioceptors, from the central nervous system, from the limbic system. All of this is going to regulate not only the cardiovascular centers, which we learned. We learned that the medulla oblongata has cardiovascular centers. It has a accelerator, and a cardioinhibitory centers that will either speed up or slow down the heart. Medulla oblongata also has the same centers for the respiratory centers. So this rhythmicity area that's present in the medulla will govern inspiration and expiration. So what exactly does the inspiratory center do? Stimulates the diaphragm, and you don't need to know which nerves. Stimulates the diaphragm as well as the external intercostals, which contribute to normal, quiet breathing. The inspiratory centers also innervate our other muscles involved, the sternocleidomastoids, the scalenes, the pectoralis minor, and so forth. So when you're taking a breath in, the inspiratory center is lighting up. You get all this electrical activity, you've got your neurons firing, And how long is it firing for? It's firing during the entire during the entire process of inspiration. So if you think about how long it takes for you to inspire versus how long it takes you to exhale, how long is your inhalation compared to exhalation? Inhalation is about 2 seconds. Exhalation is about 3 seconds. If you don't believe me, time it out. Think about how long it takes you to inhale versus how long it takes you to exhale. And again, during quiet breathing. Now let's take the other center. If this is the inspiratory center, the expiratory center is typically not firing during normal exhalation. Why is that? Well, exhalation, normal quiet exhalations, don't require any energy whatsoever. It's called passive exhalation for a reason. So naturally we're going to rely on the elastic recoil of the chest wall. We've expanded the lungs during inhalation. We're just going to passively let them squeeze down. You're going to get the diaphragm that's going to relax. We're going to, I'm sorry, it's the other way around. When the diaphragm relaxes, you're going to get compression of the thoracic volume that will release air out. That's during quiet breathing. The only time the expiratory center fires is during forced exhalation. Okay? And what does the expiratory center fire off? It fires off action potentials that will innervate the internal intercostals and the abdominal muscles, namely the rectus abdominis, causing forceful exhalations. Again, how long does it fire? Or I'm sorry, during quiet breathing, how long does it not fire for? About 3 seconds. So something has to regulate the timing of this. Inhale for 2 seconds, exhale for about 3 seconds. So you get your inspiratory center during quiet breathing. Fire, 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 stop firing for 3 seconds. Fire, fire again for 2 seconds, stop firing for 3 seconds. What regulates that? These are areas in the pons. The apnoistic center coordinates the transition between the inhalation and exhalation. It does all the timing for it. Now the pneumotaxic center works to inhibit inspiration. So if this works against inhalation, the apnoistic center stimulates inhalation. So again, during quiet breathing, apnoistic center coordinates the transition between inhalation. Turn on inhalation, then turn off inhalation. Turn on inhalation, turn it off. The pneumotaxic center limits it. Okay? So this, to prevent hyperexpansion, I'll explain in 2 slides over. What else is going to send sensory feedback into the medulla? Well, we talked about this in our cardiovascular lecture, where we had central chemoreceptors and peripheral chemoreceptors. And what those chemoreceptors are doing, they're detecting, well, central detects the changes in the CSF. Peripheral chemoreceptors are detecting the changes in the blood. And if you go back to our first neurophysiology lecture, when we talked specifically about the central nervous system, we saw that the central chemoreceptors dip right into the third ventricle. And they're testing the CSF to find out how much hydrogen ions are in there and how much CO2 is present. So that should make sense. If I have a high amount of CO2 in the blood and a high amount of hydrogen ions, what better way than to feed information back to the medulla oblongata and say, you need to increase your ventilation. Start breathing a little bit more, increase your respiratory rate, increase your tidal volume, and get more air in and out in order to unload that excess CO2. Peripheral chemoreceptors are, again, located in the aortic and carotid bodies. There we talked about the baroreceptors, where that'll detect the changes in pressure. The same, next to the baroreceptors, you'll find the chemoreceptors that will detect not only hydrogen ions, or CO2, but also the levels of O2. Because these are areas that feed, again, the heart as well as the brain. So we also want to be able to detect O2 levels. Are O2 levels adequate? If not, then speed up respiration. Increase your ventilation. So all of that, when we saw the decrease in O2, we see our chemoreceptors feeding back into our control center. Again, our control center would be, in this case, the medulla oblongata, which would then cause an increase in ventilation, which therefore will see an increase in O2. All that, negative feedback. What starts off with low O2 results in an increase in O2. The other areas, the cortex. Cortex, again, we mentioned earlier in the very beginning of our peripheral nervous system lecture. We said that autonomic regulation of the lungs, we still have some voluntary control over. So if I tell all of us right now to start controlling your breathing, you certainly can. You take over it. It's voluntary control. So the cortex has innervations into the same areas. Other things, proprioceptors. Proprioceptors that are involved in motion. So if you start moving around, that's going to send sensory feedback in, letting us know that we need to start increasing ventilation to ramp us up. Other areas, the emotions, our limbic system. Take us in situations where we're angry, or I guess maybe sad, or fired up, wherever it is. You notice when you're super angry, watch somebody. They'll start breathing a little bit heavier. Nostrils start to flare. Why is that? They're not doing anything. They're not running. Nothing's happening. But not only are we firing off our emotions, but we're also increasing the sympathetic drive. So again, the sympathetic pathways will again increase ventilation. So not only do we see an increase in heart rate, we can see an increase in cardiac output, we also naturally would want to see an increase in ventilation to increase the amount of O2 and CO2. Take, for instance, runners, take athletes, Olympics. Watch them right before, or anybody that's been an athlete, if, for instance, track. You get people that are on the blocks about to sprint. You think their heart rate is low? You think their ventilation's low? No. Everything's firing up. They've got their heart rate already up. If you measure people right before they start a race, their heart rate's already up at about 150, 160. Their ventilation, they're already breathing fairly heavy. That's all that's coming in. These are all sensory information prior to even our proprioceptors firing. That's ramping up our sympathetic drive, and therefore increasing cardiac output as well as ventilation. Other things that control respiration, temperature. So if you see an increase in temperature, that's going to increase your respiratory rate. Think about the next time you jump into a jacuzzi and listen to your breathing. All of a sudden you start breathing a little bit heavier. Natural reflex. What happens when you jump into cold? Ever jump into a cold pool? Well, maybe not jump into it, jump into something that's maybe like chest high. Jump into the pool and what happens? You stop breathing for a second. That stopping of breathing affects your respiratory rate. Again, a reflex that takes place. Pain as an increased sympathetic response. This one right here, stretching an anal sphincter muscle. I don't know where that came from. That used to be that was I took from somebody else's notes, and I remember searching through. I'm like, I've never heard that before. So I've yet now for the second time around to delete that. So just pretend you didn't see that.
It looked like someone's trolling when they wrote that.
All right, let me just throw this in. So airway irritation. Any airway irritation. If you get something caught in your lungs, if you ever drink water or something like that, and you get water down the wrong pipe, obviously you're going to stop breathing. You're not trying to get that water all deep right into your lungs. You stop breathing for a second. The cough reflex plays a major factor. So anything that comes in into the carina of the lungs, right where we split between the primary bronchi, anything that comes in and irritates the airways will stop your breathing. Again, feeds information back to the medulla to stop inhalation from taking place. Also the effects of blood pressure. Hypotension, increase in respiratory rate. Hypertension, you see a decrease in the respiratory rate. Initial response to pollutants, basically what it comes down to, your initial response, if you think about the fires that took place, all that ash that's in the air. What happens specifically to your airways? You get this extra layer of mucus that forms. That mucus is there to protect and allow particulates to bind to that mucus. Your goblet cells will start producing more mucus, and then as a response, the basal cells will start to proliferate to turn into goblet cells. Okay. Advanced response to irritation, now this is chronic exposure to, and then eventually your mucus layer breaks off, and then your goblet cells start to disappear. Why? Because your basal cells were constantly turning into goblet cells, and eventually those goblet cells, because they're constantly stimulated to create mucus, eventually die off. The asthma we talked about, So these are our bronchodilators and anti-inflammatories. This would be an example of that drug that I mentioned and on Tuesday's lecture, or last Thursday's lecture, where we talked about Advair. Chronic bronchitis and emphysema are both fall under the disease umbrella disease called COPD. That's chronic obstructive pulmonary disorder. And in almost all cases of COPD are due to cigarette smoking. Okay. So it is the fourth leading cause of death. Number one being ischemic heart disease. Number two being in some sort of infectious disease. Number three being all cancers. And then the fourth being COPD, a leading cause of death due to smoking. So what happens with these two? Even though these two fall under obstructive diseases, they have two different mechanisms. Emphysema is the breakdown of the alveoli, which results in overstretchiness of the lung. That overstretchiness of the lung prohibits getting rid of that air in the lungs. So therefore you get this increased air trapped in the lungs, you get increased residual volume, etc. Chronic bronchitis, on the other hand, is constant chronic irritation of the lungs, which results in a bunch of mucus buildup. As I mentioned earlier, due to that initial response, you get a bunch of mucus that forms, and that mucus can come up and start to cause infections in the lungs. So people that have chronic bronchitis, listen to them. They're constantly coughing and hacking up stuff. That is the production of mucus, and as a result, due to the nature of that inflammatory response, it's going to constantly produce mucus and make it difficult for them to breathe. That mucus comes in and lines the airways and causes increased airway resistance due to the reduced radius of those airways. Emphysema, here you've got examples of how that's getting broken down. We're zooming in, looking at the breakdown of the alveoli. Emphysema, again, breakdown of alveoli. Chronic bronchitis is the lining, increased airway resistance due to increased mucus as well as inflammation of the epithelial cells. Pneumonia, the last of these that I'll talk about, acute infection, mainly of the bronchioles as well as the alveoli. Due to that infection, you get the inflammatory fluid that starts to build up, and that buildup in the fluid then starts to fill up those areas of the lung. So typically they would take place in the lower areas of the respiratory tract, and very visible in a CT scan. You would see little pockets that start to form. As they fill with fluid, now you get you get areas of the alveoli that are supposed to be normally perfused and normally ventilated. Now you get fluid that fills up that area. Any of the blood capillaries that deliver blood to that area will not become oxygenated. And therefore, and typically what you would see is a decrease in their oxygen saturation. Why? Because hemoglobin can't pick up oxygen in these areas, in these poorly ventilated areas. So typically something you would see as well. So with that, that wraps up our respiratory lecture. That wraps up everything prior to exam number 3. I have nothing left to talk about on this until, well actually I won't even really be talking on Tuesday.